in theory, everything is working. Okay. So anybody in the online section, feel free to ask questions when you have them. All right. What do you guys want to talk about? Talk to, obviously, all the good stuff.
Everything.
So, what do you guys think is the most challenging part? First off, how far do you guys cover? Because I was a little...
The last chapter is the article.
Okay. I read other different because I didn't do my undergrad.
Yeah.
Okay, well, I mean, start asking me questions. I know this stuff. It's
Okay.
chapters. So if you have like a specific question on the book you have to show it to them.
Actually, the something you want to know is the strategy for the in way. This strategy.
The strategy.
Yeah.
Okay. Oh, that's tall order. Okay, so if you're just given some integral, right? You're asking me, what should I do first? Like, what should you look for? Okay, well, if you have something rational, right? With a square root. Give them trig set. Yeah. So trig set, right? Like this is a plus or minus, right? If we've got something that's rational that's like not, right? That's probably too easy, right? Like a quadratic like that. What do you think?
Wasn't like the vector of the
Okay. What? Chain rule is not exactly where I'm going with this. You would want to use partial fractions. Sorry, I would get nervous when we spell something wrong on these boards, and it would be like forever immortalized or something. I don't know. So, I mean, like, these are just a couple examples, right? So, if we've got something, like, that really is a drawing, all right. So, if we've got something with, like, cosines and sines, right? Trig reduction. Yeah, that's using all those fun trig identities that you thought you could forget, but you can't. So let's see, that's a lot of them. So partial fractions, trig sub, trig reduction. What other ways we have? We have, if we've got something like f of x, g prime of x, right? Then we all know what this is going to be. Integration by parts, right? What other ways of integrating do we know? Are there other ways? More ideas? Yeah. Yeah. So we got something like f of u. So I think that's it, right? You said integration by parts, trig sum, trig reduction. Partial fraction. Kind of a tall order, right? But these are the kind of like warning signs you want to look for. If you see a function where it's obviously got other stuff inside of it, right? Then we're going to want to use u sub. If you see something with a big nasty square root at the bottom, it's probably going to be trig sub, right? Not 100% of the time, granted, but it's kind of a good starting point to think about, right? Cool. I mean, if you've got some written out, I do not want to make them up. They will come out to be the nastiest thing you've ever tried to integrate before. Promise you. When you find an example, I'm going to give this time. Oh, no, it's fine. So, you guys all just want to write your name and student ID number on the thing? Yeah. Uh-huh.
Here.
Okay, so we're finding the derivative of the inverse at okay. So, file. So, anybody, where shall we begin? Okay. Because the important thing to remember is that we've got that formula that I always mix up where the letters go. So anybody know what formula I'm talking about?
One.
1 over prime.
Prime inverse of A. Right?
I think so. That should give us what we're looking for, right? So this is our guiding light. Okay. That looks right. I'm always scared to admit it myself. Okay. So good. If we take this derivative, right, then we'll know what we're plugging into. So f prime of x is, what do we get? Squared, right? Good. All right. The other important thing is that we need the inverse at a particular point, right? So there are 2 ways to go about it. We can solve the whole inverse and do that whole thing and then just plug the letter in, or number in rather. Or we can set this whole thing equal to 7 and figure out what x has to be, right? Yeah. Always seems easier in that way in this case, right? So we know that f of x equals 7, so, well, yeah. Square equals x equals 7, so x equals what?
0.
X equals 0. So that means that
Oh, let's choose A equals 7 or fx 7.
we're this?
In that case, it choose A equals 7, right?
Yeah.
But why fx 7?
Okay. So if we're looking for f inverse of A, right, that's going to give us some x value, right?
Oh, yes.
So this is interchangeable with having f of x equals A. Right? That's the
Oh,
right
yeah,
trick.
yeah.
Yeah. Awesome. So now we know what f inverse of A is, so we can plug that into our derivative, right? So what's f prime of 0? It'll be 7 as well, right? So our f inverse's derivative at 7 is 1 over 6. That kind of got way down there, so if you can't see it, let me know. Any questions? These are all experts. Very knowledgeable, I'm sure. Everybody cool if I change the page? Okay. Alright. Did you find some examples you want to work through? Okay. Anybody else have questions in mind? Now is the time. I'm way too excited about this. So if I get annoying, let me know.
You need that.
I'm sure.
I have one question, and I feel like it's going to be something that I'm going to be like, oh, good stuff. But, so this rule, that's like derived from, not, just by the natural law.
Yeah.
And then, okay, when I was doing that, I was getting something slightly different, and it might have just been like an algebra mistake.
Okay. So we have some letter raised to the x, and we want to be able to take its derivative with respect to x, right? So basically, this would be a case where, anybody know how to do this, like how to show that this works? I mean, we know, right, that it's ln of c times c to the x, right? Why is that? Does anybody know the justification?
I thought it was because it's the natural law, but or we said that equals y equals to the x, and then the natural law is like
Yeah.
I just did my math wrong or something.
Okay, yeah. So it's exactly what you said. Think of some y equal to c to the x, right? Then we want to be able to take the natural log of both sides. So natural log of y is x natural log c. And then we would want to take the derivative of both sides with respect to x, right? So we will get y prime over y is equal to natural log c. So we would multiply by y, right? So y prime equals natural log c times y, which was justification.
I like used the chain rule for some reason, so it was like,
Yeah, because c is a constant, right? Yeah,
that's why
there we
I
go.
was pretending it was not.
That would make things significantly more complicated.
That's why I was like,
Alright, no problem. Any other questions on this? What was the question? Okay. Goofy.
it's the highlight of my day.
Yeah.
It's this one.
So, we want to find the limit of x goes to 0 of p to the 5x minus 1 minus 5x over x squared. And it says to use L'Hopital's rule if appropriate. Okay. So, if we were to take this limit as it is, what do we get? We get 1 minus 1 minus 0 over 0, 0 over 0, right? So then we want to apply L'Hopital's because it is a fractional indeterminate form and we can do that, right? So what is the derivative of our top? Good. The derivative of the bottom, right? That x got a little one. There we go. So now if we were to take this limit, what would we get? 5 minus 5 over 0, which is 0 over 0. Drat. Well, let's try it one more time for good measure, right? So, this is also the same as what? What is this going to turn into? Let's derivative of the top. Good. And the bottom will be, oh, that looks promising, right? Because now if we take this limit, we're going to get 25 over 2, which is not 0 over 0. So we're happy. Yeah? Cool. Any other questions on that? We'll be solved, right? As long as you don't have a non-fractional form, then it's a truth. Okay. New page. What do we got? Trig sub is so cool. I think it's amazing what one little triangle can do for you.
But at the same time,
I will be honest with you, the first time I saw trig sub, it was like the beginning of life. It was not until after I'd taken my final and I had like this epiphany that I'm like, oh, I could have been doing this the whole time. Yeah.
so,
If you have an example, I will read it. Hey, wow.
You know, my magnifying glass.
Okay. Good. Yeah. We that is a plus 2. A 16. That is much better.
I didn't have one.
Okay, so that is a 16. I was like, wow, 10, that's kind of cruel. Okay. Awesome.
So, basically,
Yes. So whenever I see trig sub, I always think about what the triangle would have to be first, right? So I know what the theta is going to be there. All right. If I have an x squared plus an a squared, I know that those both had to be legs, right? So x is 1, and then the square root of 16 is the other, right? And that's the only way that we can get x squared plus 16. That's weird. Yes. So you can use this to figure out what trig substitution to use every time.
I was just trying
This was my epiphany, guys! I kid you not, is that the best thing? I did not figure this out until I walked out of my final for Calc 2. That was like the worst thing ever. I don't think a lot of them think about it. They've just done it 100 million times.
Yeah, they just don't know.
so it's X, you take this one.
Yeah, so what is x going to be if we think about these trig functions, right? Yeah, so x equals 4 tangent of theta, right? Theta, man. Okay. So, equipped with that knowledge, we can change all this stuff, right? So we also need our dx before we get too far. So
Or
theta. Okay. So now that we've got all this, we plug everything in, right? So we will get 4 secant squared theta theta over 16 theta, and then with the square root of, oh man, I didn't think that's for nearly long enough. Okay, big square root here, right? So we will have 16 squared theta. Okay. I guess that wasn't so bad. All right. And from here, anybody care to give us the next step? Good call. All right. So, I'm trying to keep up with my colors and stuff. This was like, okay. So, we'll have all this stuff the same. 16 times the 4 that we're going to pull out the square root, right? There's 1 squared theta. Okay. So, see if we can multitask. What's tan squared plus 1? Squared. Right? Yeah, so I pulled the 16 out and made that a 4. Because if we take the square root of 16, yeah. And then I just moved it over by my other coefficient so that it didn't look like I had tangent of 4 theta. So, definitely clarify. I'm just trying to make sure it all fits on one board, because trig substitution can get rather lengthy. So, which is saying something in your handwriting, I swear. Okay, So now that we've got this, we can start doing a little bit of canceling all over the place, right? We can mix these fours. Probably do that with the color. Okay. We can mix these fours, right? And then this square root and this square. Yep. So then one secant to this one, right? Okay, so let's see where that puts us before we get just scribble black the whole thing. So we've got secant theta d theta over 16 tan squared theta. All right, that is looking considerably better, right? Well, relatively better. All right, so what should we do next? Yeah, so this is where we want to pull out our u sub. So which one do we want, tan or secant? Okay, so if we've got tan, this is going to not work out as well, right?
No,
Okay, so this is not a good plan. Think again. Okay, so we're going to use this identity again.
Yeah, so would that just be like undoing
you can do it just fine.
Turn it to
Take
sine
out
and cosine.
one.
Okay,
Take that
I'm willing to try stuff. Let's just try stuff, right? Okay, so let's just change it all to sine and cosine. I'm going to pull that 1 out of over 16 all the way out. Okay. So then we can do a bit more slashing with our black one, right? So we can get rid of this cosine and one of these cosines, right? Okay. So I'm going to take this up here now. So that leaves us with, if we've just got 1 over this being reciprocal. So over 16 cosine theta over sine squared theta d theta. Right? Okay. Now this is the big one. This is why these are so long. There used to be so much stuff. Okay? So we want to pick the square thing to be our u. So what's our du? Mm-hmm. Cosine theta d theta. So that means we have 16. Okay, so then we get du on top and u squared on the bottom, which is 1/16 u to the negative 2 du. So what is our integral? Plus c. So to write that a little bit nicer, right? Negative 1 over 16 u plus c. But what was u? Okay, so negative 1 over 16 sine theta plus c. Oh, awesome. You are right. And I was just debating with myself where I should draw my next arrow to. This little corner under my thinking bubble. Okay. Over here. It's a math roller coaster now. Okay, we've moved the loop. So if we want to put this back in terms of x, sine theta is what? Based on our triangle? Opposite over hypotenuse, right? So we'll get 4 over the square root of x squared plus 16. And then we would, what was that?
Wait, right now you can 6 of 4 and 6. Rectangle, right? Yeah. But 6 and 4.
Oh, yeah, you're right. Not on the bottom. Bad ideas. Okay, let's just erase that right now. I got so excited about anything reducing in that. Okay, so we've got the 16, got the 4, got that square root. Good catch, guys. Brownie points to the front row. So, reciprocal, we've got the square root of x squared plus 16 over, this is negative 64, right? Oh, so terribly exciting. Any questions on this? This? Technically, yes, these are equivalent and they're both in terms of x, but compound fractions can get you in trouble sometimes depending on how your professor's opinion is on that. He would have probably said something in class. If he just left his like this, chances are good you can leave yours like this. But I don't sit on your class. So I'm going to simplify them as far as I can. Was it okay if I clear the page? You can leave some writing?
Just a little bit like a general,
So-
what we did, like,
Yeah. So with trig sub, basically you want to identify first, right? We said there's this nasty square root in the bottom. I want to be able to do something about that. Think about your triangle. Figure out what x would have to be, right? And then find your dx, make your substitutions with thetas, right? Reduce down, try and get it as far as you can that way. If need be, you have to do like either another trig identity or a u substitution, depending on how everything kind of plays out. And then you'll get it either in terms of theta and turn it back into x, or you'll have it in terms of u, which you turn into theta, which you turn into x. Unless, of course, it's a definite integral, and then you just get to plug numbers in, which is great.
so when you switch it back to that,
Yep, so the triangle is double handy.
so in the exam, can we just draw?
I don't know why you couldn't draw It's not like you're cheating. You're just identifying what's in the problem, right? Yeah, so for all you guys who came in late and missed the really awesome thing about triangles here. Okay, is it okay if I make a new page just to talk about the triangles? Okay. So, as I was saying, this is something that I realized when I was walking out of my Calc 2 final, when I did this. So, like, let's say that we have a square root, right? So we've got x squared plus a squared. Well, if I think about what a triangle would be, and I think about Pythagorean theorem, right? If I have two squares added together, that means that they must have both been lengths of the original triangle, which makes my hypotenuse that square root of their sum, right? So then you have to think about, okay, what if I have x squared minus a squared, right? What does that mean? Well, that means that my x must have been a hypotenuse, because otherwise I wouldn't be doing that, right? Then you would make a one of your legs, and the other leg be that square root. Right?
So now the theta is,
Yep, and then theta is always this one. Great. And I mean, these ones can switch around, obviously. I can't remember which one is supposed to be which, but one has to be the leg. Just depends on which trig substitution you're going to make. So, and then the last case would be if we have a squared minus x squared. What do you guys think? What's my hypotenuse? Right? And then pick a leg, pick a leg. Triangles are the best thing ever.
so,
Yeah.
see the tree.
Yeah. Okay. So is everybody cool with this? And everybody became late finally, right? Excellent, guys. All right. So what else you got for me? I'm gonna check anybody in online question, ask question too. Oh,
Can you see us or they can only see
They can see what I'm writing and they can hear whatever gets picked up by this little microphone here.
Hello.
So they all say hello. Anthony is in our online section today. Okay, so to answer your question, the 4 in the denominator of that last problem that I just cleared off and is on a previous page had to come from when we reversed the triangle with the trig sub. Did you figure that out later, or? He's typing. It takes a little while for him to stop. Oh, did I type that? No, I'm just on the chat. That's okay. All this tech is like, I get so terrified that I'm gonna like cut something off, or it's not just like you guys are all in the room. There's other people that I'm accountable for. Okay. Okay, so he's got Okay. So does somebody have another question that they want to talk about? Yeah. Okay, there's lots of questions. I will pull up that sheet again while he's, Okay, so there should be a way for me to go in my other pages. Those are my pages? Those are my pages. That's my math roller coaster. Okay. Okay, so he was asking how I decided to go from sine theta to this, right? And that comes back to this triangle. If I were to think about sine, that's opposite over hypotenuse. And the opposite is going to be the square root of 16, which is 4. And the hypotenuse is that square root again. So that's how I'm coming up with that resubstitution in terms of x. So does that fix your question, Anthony? Yes. Excellent. Then we will do more questions. Okay. Insert a blank page. Woohoo! Okay. See what question? Okay. Definite interval. Okay. All right. This is what we have. We have an definite interval. Is it a 61 or a 67?
That's
I guess it doesn't really matter, does it? All right. Well, we have a number. X squared over 9 plus x. Okay. So the question asks us whether this is convergent or divergent, right? So where shall we begin?
Well, let's first factor out 67, so that's.
Yeah. You don't really have to worry about this. It could easily be a 1, right?
And is this the actual like one of specific value, or can we get this? Like is it the x squared is 1, and then we can go 1 over x to the 4?
Yeah. All we have to ask is whether it's convergent or divergent, right? So what he's suggesting is that we can kind of make like a comparison. That this is like 1 over x to the 4th. Because when we get really big, right, for x, this 9 isn't going to matter. And then we're essentially looking at x squared over x to the 6th, which is like this, right? So if we're looking for just convergent or divergent, we can make this comparison and be able to tell. Yeah?
The kind that I realized about 1 over x is that only 1 over x is the one that supposed to specifically over any other x.
You're exactly right. This power is p, right? And if p is greater than 1, then it's convergent. Oh, that's the wrong way.
Like twice as much area.
Other way.
The way it's
P is greater than 1.
yeah, very
Implies.
Because if we have,
Wait, it
Yeah.
approaches.
It should approach 0.
Right.
Oh, right, I got it.
So if we have to show something, focus on the limit.
Yeah.
Or
so if,
angle.
yeah, so like this is kind of like your thought bubble of what you know you're gonna get to, right?
Yeah.
So if you wanna actually show your work, limit I choose R. Right?
And you was really concerned with me for a second. I was like,
You always look together.
okay, good to know. So from here, what shall we do? Not really gonna fix anything, right? Because we don't have any absolute fits.
Yeah, I'm in that.
Or the limit is one of the infinity here.
Yeah. Okay,
Is
so
that reasonable?
That's what we were just kind of discussing very quietly here, because you have to remember that there's somebody trying to listen to this. Yeah, so the suggestions that we've been getting, right, we can ignore the 9, just like we kind of did here, and then like to,
So all we have to do is write a limit before that, before the.
yeah. Well, and I mean, the technical thing that we're doing is we're saying that this is always less than or equal to the limit as R goes to infinity of negative R to R over S. That's the key part that we're missing, right? Because if it's going to converge, right, then whatever is below it will obviously converge as well. So as long as we can pick an upper bound that is easier, we can just integrate that, right? So then we would say, okay, the limit as R goes to infinity, we would do this integral, 1/5 x to the negative fifth, evaluated for negative R, or, yeah. So.
So 1 over x is the one that's divergent.
Right, because when we integrate that, we get natural log, and
Got it.
it approaches infinity,
Right, yes.
right, and it's just,
Wait, that's what I got.
How big is the last thing?
oh, this is the third, by the way, and this is the 3, because I subtracted, so added, just there.
Okay.
Okay, so I did this integral, right? This is x to the negative 4. So if I add 1 to that power, I get negative 3, and then this would be negative 1/3 out front. That got really, really sloppy, so I should probably just rewrite this last bit. Okay, so negative 1/3 x to the negative 3, negative r, right? And then if we were to actually plug this in and do the limit, we would get 0, right? Wait, would we? It's just kind of, oh god, what is that? Why do I have that? Go away. Okay, I bumped some kind of button. We're not going to bump that button again. So if we do this, negative 1/3, we would get x to the negative 3, or r to the negative 3. Yeah, that's fine. Yeah. Okay, let's just do this. Because I'm gonna like debate with myself all night about this if we don't just do it. So humor me. So we got r to the negative 3 is still a limit as r goes to infinity, right? And then this is gonna be plus 1/3 negative r. Yeah, that's why it works. So then this one is going to give us 0, and this one's going to give us, oh, no, because, yeah, so,
Divergent means there has to be an infinity somewhere.
Yeah.
Just remember in
So as
class
long
when you
as-
said we get a infinity and he said screw it.
number is good, infinity is bad, right? number implies convergence, infinity implies divergence.
So 1/x.
Yeah, because the antiderivative is natural log rather than another exponent. So that's why that one diverges.
So anything higher than that.
Yeah,
Yeah,
so,
so that's
so
what
if
this,
it-
this is, that's
if
what
the
this is about.
exponent is lower than x to the negative one, then it converges. If it's x to the negative one, it diverges.
Yeah. So this is the idea.
That's just,
So if P is
you
greater
can only
than,
use that if it's like, if does a diverge or converge, really quick question, and then yeah, other than that, it's not helpful if we actually have to do it.
Oh, what's the state? What's the state if the p equals to 1?
if it's equal to 1, it's going to be conditionally convergent, but that's not something you're talking about right now. That would be more applicable to series integrals. So it's divergent.
But if the interval is
If P is less than or equal to 1, it diverges.
if the p was 1 and the interval is minus infinity to the infinity, but
Of,
it's also
natural
divergent.
log, right? So the negative infinity is undefined, and so then it's a divergent integral. Because, like, if you think about what the graph of natural log looks like, right? We
Yeah.
can't approach negative infinity, right?
Yeah.
Yeah. So 1 over x could have that as a limitation, but the function would be undefined over here, so then we would have undefined integral to be.
No, I think if the x also are close to the infinity, 1 over x also is 0.
Right. So, like, what you're saying is p equals 1, right?
Yeah.
So we have the natural log of x evaluated from negative r, right? So this one, yeah, we'll get infinity for that first bit, and then we'll subtract undefined term. So it's infinity.
Oh, where is the undefined one?
If we have negative anything inside a natural log, it's undefined, right?
Oh, yeah.
Yeah. So like even if we put 0 here, right? Then this is going to be going to negative infinity, and that's still like an indeterminate form. We would have to do sort of figure out if it's conditionally different. Yeah. So that's what I'm talking about. But honestly, that's quite a bit into this. So any questions on the easier couple that we started with, rather than the natural log debate?
What about
Solving for
Oh, well, I'm saying, yeah, when I told him that, if it's x to the negative one, any lower exponent, you can assume it diverges, right?
Yeah.
But when we have, that's only if it's, an approximation from like x squared plus 9x, we want to know whether it diverges or converges, where we can just knock stuff out and rewrite it.
Right.
And we can but we have to include the less than in our proof.
yeah, this is the key for knocking that stuff out. Is the
If we don't put
Finding
the
the
less
other
than, then we're wrong, because that's an approximation.
Because the idea is that if we can find a convergent curve that is close to this or above this at all points, then we can use this as an approximation.
And so I'm saying that that's useful both only when we have like 1 over x and a negative or 1 over x and negative 3. I have a reciprocation problem where we do diverges, and you actually have to find the derivative.
Oh, wait, do you have an example? Is it okay if I clear this page?
Yes.
Okay.
I have,
These are good questions.
I have these. They're not ridiculous.
Alright, so do you have a particular favorite?
What?
Do you have a particular favorite?
Oh, that was just a recitation, and I was smart enough.
Oh, well, there you go.
No, that's
Okay. So we're just, all of these
Seven.
are about convergence, or there's just, it's just doing the integrals?
I don't.
Like,
I don't know what you call it.
Wait, do we have the football one? Is that one on there?
No. That was not good.
Yeah, but if we know how to do that football one, we can take on any.
if it's not gonna be on your test, we can come back to it at the end, but but we would have to answer all the other
Oh
questions.
my God.
Like when you're actually.
Yes.
So, actual
I'm
question.
missing a third. No, she reduces the zero. So, no, this, I'm missing one, so that's 66.
Oh, I
I'm still
mean, this
paying
one's
two.
just-
I'm not-
Okay. Okay. So, if we have this, right? So if we
Take a picture of the, oh my God.
want to do that,
You want to take a picture of them? Because the recitation problems are impossible for you. Solving the actual test, it'd be like, oh my God, they studied all of that for nothing.
okay. So if we have this, what is the antiderivative? Not tangent,
Inverse tangent.
inverse
Sorry.
tangent.
Sorry.
Oh, I'd rather have that limit as r goes to infinity. Okay. Tangent inverse of x evaluated from negative r to r, right? Okay, so that means we have, I mean like, kind of have. We can't really plug in infinities, right? But we're gonna kind of think of it that way, just for the sake of writing this somewhere. Okay, so here is where I would think about what the graph of tan inverse looks like, right?
Yes.
Like this. And these are asymptotes?
At, I have 2 and negative pi over 2.
Yes. Okay, so then we know that at infinity, we're going to get pi over 2 minus negative pi over 2, which gives us I.
Yes. And that sounds good. The area of like this pi with it.
So, what do you do a problem with that? You basically getting anti-derivative.
Finding the asymptotes of that one.
Well, not necessarily.
Well,
I like
with
to
an infinite one, it would have to be asymptotes from this. Because if they're not asymptotes, you're going to get infinite values, right? So if it's not an asymptote, it's divergent. Yes.
So, all those problems.
Yes. Or you would have to say divergent and then each step, right? Because usually the question will be evaluate the integral if it converges. If not, say diverges. Yeah. Yeah.
What trigonometric mental graphs would you recommend?
Trigonometric mental graph.
Well, see,
Oh,
like that.
sorry, that was just a really great phrase. Yes.
It's because, see, off the top of your head, if you don't know what it looks like, you're sort of screwed. Like for the
Yeah.
1 over x squared, even though they're very similar, they're completely different. So I can understand when not knowing the graph there is, you know. But for trigonometric functions like this one, if you didn't know the graph, you sort of
This is the only one that has nice infinite asymptotes. So,
Oh, okay.
If you did say fast, you know, time, you can really well, because I didn't
So, okay, so
okay, so sine and tangent.
I had a, I'm sorry, I had a physics test that day, and that's all I was studying.
Yeah. Now I wrote it down. No influence for sure.
So tangent
He
and
said know all about it. That's what I wrote down. Know all about
Oh,
sine
God.
inverse and tan inverse. So he wants, I think he wanted to know the aspect.
No, it's not. It's not.
Where's the asymptotes of
Sine inverse, I don't actually know what's the time of it. Right, because that's going to be,
It is kind of, it kind of,
well, because, okay, so if we're talking about sine inverse
but
of x, right? So, do you know what it looks
I
like?
think it's like
It's basically like
this. But I'm not really trusting myself because when I
Okay.
did my notes.
Well, let's think about what you've got down, right? So pi over 2 gives you positive value, so that makes sense, right? So we want it to be 0 at 0, and we want at pi over 2, or at 1, it should be pi over 2, right? or which way does it go? X is 1, right? This is pi over 2. Okay, so the bottom will be clearer, I promise. So at -1, this should be negative pi over 2, right?
But
And so then that's the sine inverse on
Oh,
17,
really?
right?
So
Yeah.
it's from.
Because if you go around more than that, that's not going to work, right? It's no longer a function. If we try to do more periods in this, because it would essentially just kind of like wiggle along the y-axis, just like it would along the x-axis, right? So,
But the domain.
and that makes sense, because that's the range of sine, right?
Yeah. Yeah.
Yeah.
Use inverse.
See what I mean there? The problem comes in with the domain of x, right? If you're talking about that, was all remembered to all the way around the unit circle. But the range of sine inverse is only from -pi over 2 to pi.
So for, and just how like it has boundaries, it's pretty much like the same as this would be y on the x-axis.
Well, because tangent can be more than that, right? Because sine and cosine could be anywhere between -1 and 1.
Oh.
So you can make as big a fraction as you want. That's
Oh,
why.
that's why I can,
That's why when we look at the graph of tangent, right?
it can be different.
Yeah, it has asymptotes like this, because we can have infinite y values for tangent. And then it's like a piece, right? The idea with if you know the original trig functions, you can just rotate them and get the inverse function, as long as you know where to constrict the domain range. Okay?
How the domain of the reverse of the sine is minus pi over
You mean the range?
2. The domain. Is there a domain of
Because the range is the y values and like the y-axis, right? And the domain is the
okay, the range, sorry.
yeah. That's what we were discussing here. Like normally, sine can be any value along
Yeah.
the unit circle, right? But in order to only have a function rather than repeat, because technically, like this would have gone up
Yeah.
like this forever. But to make it a function, we have to restrict it to just this square, or it's no
Because-
longer a function because
So
we'll
you-
have multiple y values for every x.
So this
And
is
so-
a
the one-to-one
general
rule.
rule for that, right?
yes.
is it the 101 rule? Is that what that is?
Yeah. I think so. Yeah. Because we would want, yeah. Yeah. Okay. Okay, back to this page. We've had a really in-depth discussion about trig now. Okay. What else? We got about an hour left. So.
This one.
Okay. Oh, Jesus, that's right. I'm sorry.
Sorry.
Is it partial diffraction?
Okay.
Is that what we're doing?
I'll keep straight. Right?
Yeah.
Okay, and we're just supposed to integrate this, right? This is the plus sign, by the way. It kind of got mutated. We're just integrating this. So what should we do?
Oh, I just like getting rid of constants.
Okay, if
Because
we can pull it forward to the outside,
it's,
sure.
it's like one of those traumatizing things, you know, it happened once and you're traumatized forever.
Okay, I can understand that.
So can we just take that for a while? Or if we should have some do it with it. Yeah, that's just
Sweet.
like,
You can't do it. You can't have an integral inside of a natural arc, or whatever shenanigans that just sounded like to me.
yeah, you.
Okay. And this was the question, right? I copied that down.
Yeah.
I don't.
We have to like get 6 people
It's
to
all-
corroborate this.
Yeah, it's enough.
It's the new, so this is the new guy. Yeah.
Oh, This is why design the homework,
Uh-huh.
but I don't publish.
Okay, but is this kind of question on your test?
I know. Wait, one second.
So like if this isn't gonna be on the test, then we can assess this in the arc another day.
Or 7
Okay.
Yeah, that would be.
Okay. Well then,
Yeah.
so the only other thing. Right. Whether that's helpful or not, it's just a new perspective. Because we can't use a U substitution because we don't have another e to the x. We can't use partials because it's not linear or quadratic or
Are we
polynomial.
supposed to just find the integral? Or figure out a way to do this?
So just find the integral. There's no limits of integration. So
Just
oh,
No, you can't.
yeah.
It's
Okay.
not the x power, it's equal to vary, so if we have one, yeah,
Okay.
Yeah, like this.
So what's du?
x to the n to the x.
Okay. So what's dx?
One. Right,
Right.
right.
And what's e to the x? Oh, it's minus. It'd be creating, which is something mathematicians are not usually known for. Although, if you look at all those proofs that we have, some of those are pretty creative. Okay. So now that we have.
Should we get into a Taylor series? Taylor series makes up 90% of that.
I don't know why.
Okay, it's like a proof. It's a really nice way to prove. Really nice.
Okay. Anyway, so now we want to try and rewrite this, right? We've got 1 over u, and then this will be times our du over u minus 4, right? So now what should we do? It's just lovely. Bless you.
Multiply it and use 1 over u squared minus 4u.
We don't have a derivative on the top, right? So natural log is a no-go. So since you have the solution open, I will let you tell your classmates what to do. Do you think you understand it?
Only.
Is there another substitution and integration like that? Is there another substitution like minus?
Yeah. Yeah, we'll put the, oh yeah, okay, so, or, actually, so, this is equal to, so this is the side, right? Okay. So if we have 2 linear terms in the denominator, partial fractions. So a over u plus b over u minus 4, right? So then we get a u minus 4, a plus b u equals 1. no, this has to be equal to that. So then that means B equals 1/4.
So what you do is you put in 0 for u, and you left a -4 is equal to 1/4. Okay.
So there are lots of different ways you can look at it. The cover-up method, which he just described, you would pick u equals 0, right, which would eliminate the b term, and then we would just figure out what a would have to be, right? Or vice versa, if we say that u is equal to 4, we would figure out what a had, or what b had to be. Or the way I do it is to think about like a linear system. So I know that negative 4a has to equal 1, and I know that a plus b has to equal 0. So it's easy enough to solve for a, negative 1/4, and then b has to be the opposite of a. So it's because I know that if I were to make a common denominator, which is what we had, the top has to match, right?
Okay.
So a times the bottom of this one and b times the bottom of this one would have to equal 1, because that's what we had on top. So then you can say, okay, I know that I had no u terms, right? So u has to equal, or the coefficient in front of u has to equal the coefficients in front of u on the other side. If you don't learn that way, it gets to be a bear, but that's how I learned it.
Can I plug in, for example, since we did this stuff, can I use already a set term and I came up with something to do with it? Because what I did is, in my head, what I did is I put u equals 0 to cancel the a.
Right.
Can I do that?
Well, I mean, that's called the cover-up method.
Oh.
Yeah.
Oh.
It's one way to do it. Obviously, like, you can't say that u is strictly equal to this, but in the case that u is equal to 0,
And-
what did we have left?
Okay.
So that's basically what you're saying yourself, right?
Well, no, but now I, yes.
If your brain always used proper mathematical notation, that's what it'd be saying. Okay, we all know that we have that going on inside our heads, right? Just agree. It's okay. Okay, so then we still have this integral, right? So negative 1/4 over u plus 1/4 over u minus 4 u. And now each of those is a natural log, right? This was me making my common denominator, right? So like multiplying each of those and then just distributing. Like I said, my method is not your method. If you found a method that works for you, great. This was just another method that you could use if it helps. Okay. Cool. So now that we have our slightly more friendly integral, what are we going to get? Let's see, right? Or it won't be squared, right? No. Yes. Okay. So now we want to get all this distributed into, right? So we'll actually have
No, that's
the natural log
u
of
minus 4 minus u. Yeah, there we go. So it's not you. I would. So in this case, if you're gonna distribute first and then rewrite, right?
Yeah. So now that we've got this going for us, we want to make sure we get this back in terms of x,
Right.
because we kind of forgot what we were doing here. And then, so u was that. So we've got the natural log of 1 minus 4 over 4 plus e dx plus c. No, because we have an additive term.
Oh, okay,
It's good to have somebody to keep me on my toes.
gotcha.
Mutual then, okay, so I'm gonna check for online questions. Okay. So any questions on this page? Okay.
That was,
Yes, that was a partial fraction decomposition.
that's because of its, function.
Yes. So we had a polynomial term in the denominator that happened to be a linear term times a linear term. So that's the decomposition. Do you guys need a review on the different types of linear, or of partial fraction decomposition? Like, I mean, there's the irreducible quadratic term, like you guys
Oh,
always
so
talk about
like-
linear?
Example, but
Like ax, what, like a squared
Yeah.
plus b.
Yeah.
anyone going to start with something that's really complicated and then that's like you can division and use this, you just do that
Yeah,
just
a
a bit
reduce.
more.
Yeah, okay. Do you have an example like that, or?
I think the one he did was 2x third plus x squared minus 100 over
Oh, 2x to the third.
plus x squared
I should try to make sure that this is legible.
minus 100 divided by x minus 2.
Okay.
Oh. That's what
Yeah.
So it's plus
I would.
It doesn't really matter.
It doesn't.
You trust
I don't
I
care.
trusted you.
I just didn't know if it would
Does it?
Well, it matters by like a simple factor of -1.
Yeah,
so don't
it's-
fuck with a fraction.
I'm not gonna make a huge difference. So, okay, so this is an improper, right, improper rational function. So we would have to do the long division. Squared minus 100. And I know that this is the piece where you can do synthetic division,
Yeah.
but I don't remember how to do synthetic division ever.
Really? It's like a million
I
things.
don't know. That's what I was gonna.
Okay, well, if somebody could refresh my memory on how to do synthetic, that'd be cool. But because I know it has to do with like remainders
What's
and
the you need to cancel the x third?
The highest, I don't know how to work it with the x is -2, but I know if it's,
well, it's like the whole point is that you have a term here.
so x minus, yeah. Is it -2, just -2, 2, 1, -100, bring this term down automatically, and then you multiply, 2 times -4 is -4, minus -3, -3, -6, and +6.
Well, let's find out.
So,
Okay.
I-
So,
We'll take my word on it.
all right, we're gonna go with long division. Yeah. So in order to do this first term, right, we want to make sure that we get whatever it takes to make x squared or x be 2x cubed. So we'll multiply by 2x squared. So we get 2x cubed minus 4x squared, right? So if we have minus this, so these will cancel, and then we'll get x squared minus negative 4x squared, so that'll be positive 5x squared minus 100.
Why not?
Well, that's up to x. That should be 0x.
I mean, yeah, there's a plus 0x. It will matter in this term, I
That
guess.
would matter.
Technically, yes. It's mathematical on Jimmy. Oh, God. Smart boy, yeah. Oh, yeah. Okay. Now that we're back, I'll check it. So, yes, technically there's a plus a 0x term here, which will come in handy when we talk about this next step. But I wasn't going to worry about it just yet.
Yeah.
You don't
Alright.
have to worry about it up until you'll just go to get to there.
Yeah, so now the point is that we want to match the 5x squared, right? So we add the 5x. But so that's why it's going to make a difference, because we'll have an x term here that we wouldn't have anything to subtract from. Which, I mean, if you subtract from nothing, it's just better to have a placeholder, I guess. So minus 5x squared minus 10x. So we'll get a positive 10x minus 100. Okay, so then the final term is 10. So we'll minus 10x minus 20? Well, I mean, it's minus minus, right? It'll be plus. I just try and keep my notation clear. So we should get negative e, right? And basic arithmetic, you know. Okay, that's an 8. All right, and so then that's going to be our remainder. So that means we've got this whole thing, right? 2x squared plus 5x plus 10, and then minus an extra 80 over our original term. Yes? Okay. Really, my enthusiasm is waning, and I don't know whether it's a good thing or a bad thing. Okay. So now we integrate term by term. So the first one, polynomial stuff, is not so bad, right? So we'll get 2/3 x cubed plus 5 over 2 x squared plus 10x. And then the last one is going to be a natural log, right? So whatever he did was wrong, too, by the way. If you were paying attention to what he did with information. That was no good. So, yeah. Because that's supposed to, the idea is that the end is supposed to give you the remainder that you're supposed to get, and like each one's supposed to give you the coefficient, and that did not work the way he was doing it. I can never remember how it works. If you Google search it later, it should be a quick study, but I always just go with what I know and do long division. And everybody loves long division. Everyone. Okay. Everybody clear on the screen? Cool. Cool. All right. What else? I know. How to spend amazing that. I think that's what makes it hard. There's just so much in Calc 2 you have to learn, and you guys are even halfway done. I don't mean to sound discouraging, but
Yeah, my friend does that with Calculus in the hobby.
it's considered like one of the most difficult classes anywhere, anytime, no matter what you do. It's okay, but see, once you get past this, you're like, well, it's all downhill from here. Yeah.
Please, thank you.
Yeah. You guys have a good night. So, other questions? Because we still have 45 minutes.
Okay.
I'm not going to take your exam. That is unethical. See, now I have that on recording and everything. So, yeah.
I don't know.
So, do you have any questions? You just said 5 minutes version the whole time. Okay. What you do? I'm just checking, making sure. Pulling you out of your comfort zone.
Can you do another one? And I have an example of it, just like one more.
Of the improper one?
Yeah, the two
Oh, yeah, so that was an area
Yeah.
to look like that, so that one's good. Okay. Okay,
So I
so.
have it, it's easier if you do it.
X cubed plus x squared plus 5x plus 16 over x cubed plus 4x dx. Okay. So, because this is the total degree on the top is equal to the degree on the bottom, we're going to have to do long division again. So, got x cubed plus 4x, and we've got x cubed plus x squared plus 5x plus 16. Okay, so what should we multiply by? 1. It seems kind of trivial, but okay. So we got x cubed plus no x squared, right? Plus 4 x's plus no 1's. Subtract that whole thing. So we'll get just x squared plus x plus 16. Right? Okay, so that makes our integral be 1 plus x squared plus x plus 16 all over x cubed plus 4x dx. Okay, having fun now. All right, we want to look at our denominator now because, well, actually, first thing you want to try is see if this is the derivative of this. If it is, then you just have natural log and you're done, right? Unfortunately, we are not that lucky tonight. So, yep, if the numerator is the derivative of the denominator, you say natural log, and you're good. Mm-hmm. Yeah. Natural logs are easy, in my opinion. They're not easy for everyone. But. Okay, so since we do not have that case, we're going to have to start looking at how to factor out the bottom, if at all possible, right? So how could we factor the bottom? Okay, so we've got x squared plus 4, and the top stays the same. Okay. Is there anything else we can do to factor the bottom? No. So this means that we're going to have one of those irreducible quadratic forms when we do this partial fraction decomposition, right? So we do another side thought. We've got a over x. And then does anyone remember how to do the numerator if we have an irreducible quadratic? Ex plus c, perfect. Okay. So then, depending on how you like to do yours, obviously you're going to have a different setup for this. I'm going to do the thing again. So I'll go through it slowly this time though, so you guys can learn a different method in case you want to know more things. Okay, so we want to multiply a by the denominator of the other fraction. So we'll get ax squared plus 4a. And then we want to multiply this x times the numerator of the other fraction, right? So we'll get plus bx squared and then plus cx. And as before, we want this to equal the numerator of the other fraction, or of our original fraction, right? So x squared plus x plus 16. Okay. Yes, these two things will be equal. So now we can just look at coefficients, right? So first we think about the x squareds. So we know that here we've got a plus b, right? And in our top of the original thing that we're breaking up, we had a 1, right? So we know a plus b must equal 1. Yeah. So if we look at our x terms, what do we got? What over here has an x on it? Okay. And that should be equal to what? 1. And if we think about our 1 spot, and that should be equal to, okay. So this one tells us that a equals 4. This one, obviously, c is just 1. So if we know that a is 4, we've got 4 plus b equals 1. So b equals, good. Now that we know all this, we can redo our integral, right? So 1 plus a, which was 4 over x, plus, now we do our b, negative 3x plus 1 over x squared plus 4 dx. Okay. So now, integrate term by term, right? I'm going to kind of box our long division. Okay. Everybody take a deep breath. Alright, so we'll get x, right, plus 4 natural log of x, and then this one. This one is where things get a little bit trickier, right? So let's just leave that for now. So we'll do, and 3x plus 1, or x squared plus 4. Okay, so what can we do about that last interval bit? Good thought. We don't have a radical though, so we don't want to do trig stuff.
So you're substituting.
Maybe. Okay. Well, let's kind of think about it, right? If we picked u, it would have to be the x squared plus 4, right? That would make our du what? Okay. So, is there a way that we could get this to work? Based on what we haven't been doing. Because now our integral, like our hypothetical integral, looks like this, right? Just plugging in what we can right away. Is there any way that that's going to cancel out? No. You only get that
Split.
one. No. Okay. Well, I mean, if you explain it to us, then you're going to learn it too.
Okay.
So explain it.
So we split it up, we have the negative 3x plus 1 numerator, we have that integral negative 3x over x squared plus 4, and equal 1.
Okay. So for right now, I'm going to get rid of this so that I have to write linearly. Okay. So taking this, you're saying we'll leave all that first bit the same, right? And then plus, we'll split this into two more integrals, 3x over x squared plus 4, and then 1 over x squared plus 4. Dx on each of those, right? So like we said, this one will work out okay-ish with the u substitution, right? So what did I give us? Right? Right, and now how about this one? It looks kind of like, we said about the trig stuff, right? But it's no radical, so what inverse trig function doesn't have a radical inside? Sine does have a radical. Inverse tangent. But inverse tangent usually has a 1 here. So what can we do to alter that? Okay. So, I'm running all out of space. So I'm going to use a different color and just wedge it in somewhere. Okay, so this is kind of what we're thinking about, right? Tan inverse of x usually gives us 1 over x squared plus 1, right? So what if we had something else other than just x in here? What could we put that would give us a different derivative here? I mean, we could do trig stuff. It's not going to hurt anything. Would you guys rather do it that way than doing it this way? This is kind of messy. Okay. We'll do a trig sum. That's fine. Okay. So back to blue. Think of our triangle, right? So if we have a sum, we know that the square root of x squared plus 4 is over here. And then we've got an x